Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In the last lecture, we started discussing some approximate methods in quantum mechanics using which we can solve those problems which do not have an exact solution. In particular, we are talking about the systems where we have more than one electrons. For example, any atom with more than one electron, or for that matter any molecule with more than any molecule having electron more than one. In those cases, we cannot find exact solution of the Schrodinger equation, and we first looked at the one of those methods known as variational principle. In this principle, we discussed that suppose we have a Hamiltonian whose exact ground state psi 0 and whose exact ground state energy E 0 we do not know. In that case, what we can do is that we can make a guess, we can define a trial function, we call that phi, and evaluate an energy corresponding to this trial function, and we call this trial function as E phi. What variational principle guarantees me is that this energy that we get out of this trial function, we call that E phi, is always going to be greater than, or at the best it is equal to E 0 or the ground state energy. So, when E phi is equal to E 0, to that limit, the phi, that the guess or the trial function that we have taken is representative of the true ground state solution or the true ground state wave function psi 0. So, in the limit that E phi goes to E 0, our phi, the trial function, becomes a psi 0 or the ground state function. So, this is what variational principle told us. Then the procedure that we would apply using which we will apply variational principle is as follows. We will define the trial function and we will define a variable in this trial function that we would call alpha. So, phi will be a function of alpha, just to remind you. So, if I say phi is a function of alpha, therefore, E phi. So, when I do calculate this integral, so you would see that I would integrate all other functions and then I will be left with E phi will be a function of alpha. Now, I know that E phi, the trial energy, is always going to be greater than E 0. So, if I can minimize this E phi with respect to alpha and solve this equation, then I can find at what value of alpha this equation holds good, and I call that value of alpha as the alpha minimum. Once I have this alpha minimum, what does it tell me? That this value of alpha corresponds to the lowest energy given the trial function you have. So, therefore, I put this alpha minimum into my phi function. So, this becomes my best explanation to the ground state energy. And what is the energy? So, energy E phi as at alpha minimum is the best explanation to E 0, and phi of alpha minimum is the best explanation to psi 0. So, of course, when we are looking at variational principle, it is very important that what kind of trial function we are taking. For example, just to give you an idea, suppose the psi 0, of course, in this case I do not know if a Hamiltonian is very complicated, I do not know its solution. Suppose, remember, my Hamiltonian is the simple particle in a box problem. In that case, psi 0 I know they are sine functions. But suppose I would pretend that I do not know that they are sine function, I would instead use suppose an exponential function for the trial function. So, I will call that as e to the power alpha x or e to the power minus alpha x, or suppose I consider it as some polynomial and I call as x to the power alpha. So, these are my different trial functions. Of course, if I make a choice of trial function, I can always evaluate E phi corresponding to that trial function and minimize this trial function with respect to alpha. So, if I am thinking that my solution is supposed to be an exponential function with a positive exponent, or a solution with a solution should be an exponential function with a negative exponent or x to the power alpha, I do not know what value of alpha should be, whether it is 1 or 2 or 1.5 or 1.7 or 2.9, I do not know. So, in that case what I would do is that I would simply calculate E phi, which will be a function of alpha, because I would integrate out all these x, because these integrals will be evaluated over x values. So, therefore, the energy will be a function of alpha, and I will minimize this energy with respect to alpha and find the best value of alpha. So, the best value of alpha will give me the best explanation to the true wave function, and the best value of alpha will give me the best approximation to the true ground state energy. Of course, if my choice is bad, my outcome will be bad. If my choice is good, I can get very good results from variational principle. So, a lot depends on what is my trial wave function. Okay, we will now look at one example. The first example is we will look at the variational principle, how we can use variational principle to solve hydrogen atom, but you would say that okay, we have solved hydrogen atom exactly. So, that is actually the point. Let us consider an example where we know the exact solution and pretend that we do not know the solution and start with a different trial function and see where we can get. So, this is the Hamiltonian of hydrogen atom. So, this is the first term, the kinetic energy, which is minus a square divided by 2 mu, and the Laplacian term. Laplacian has some radial part and Legendre term. So, then I write this Hamiltonian in atomic units. So, where you see h bar is gone, mu the mass of electron is gone, and then the potential energy between the electron and nucleus. So, because this is hydrogen atom, so we have one electron and one nucleus, and in atomic units this is simply minus 1 over r. So, this is my Hamiltonian, and in fact, I should remind you, I know its exact solution. If you remember, the exact solution for the ground state wave function for hydrogen atom was some constant multiplied by e to the power minus z over a into r, or essentially it was the true ground state function was e to the some constant e to the power minus z over a multiplied by r. So, which is in case if I want to write it in the atomic unit, some constant multiplied by e to the power minus r. So, this was a function of as to e to the power minus r. R was the distance between the electron and nucleus. So, this I know, but what I would do now, I would take a trial function, but this trial function I will say that okay, suppose I do not know that this function is e to the power minus r, rather I will consider it some e to the power minus r square. So, you see that I am changing the functional form. So, instead of an exponential the exponent as minus r, I am considering it as minus r square. But what I have done is that I have given a parameter alpha, so that I can see what kind of alpha I am getting out of it. So, I know to begin with that this is a somewhat not a very good choice for the wave function, because the true wave function has a e to the power minus r dependence, and my dependence itself is not so correct. But let us see what we are getting. If I have defined my phi, I can always obtain this E phi, which is I have one energy integral phi h phi, phi in the bra and phi in the ket. If you want to look at the term in integral form, this is written here. So, remember my trial wave function, I am only considering the radial part. So, that is no term in angular part, but just to make it complete. So, I can this integral will have terms with over r. So, with an integral of r square dr, I have term with sin theta d theta and d phi. So, when I integrate these two terms, I will get 2 into 2 pi, which gives me 4 pi multiplied by this radial integral. Similarly, when I look at the overlap phi star phi, in that case again I am doing it for the angular part. I have 4 pi here multiplied by the radial term. So, since phi is e to the power minus alpha r square, phi star is also going to be same, because this is a real function. So, phi star phi will become e to the power minus 2 alpha square minus 2 alpha r square multiplied by r square. So, all these integrals that you would find here will satisfy this form shown here. It would have x to the power 2 n e to the power minus b x square, and in such a case we know how to evaluate these integrals by following this. So, given that we have these two integrals, let us say if we use this relation, we have this outcome. You can do this on your own, this is not very difficult. So, I say that the first term over here gives me terms like this. Let us look what are there. Of course, when I am integrating over all values of r, theta and phi. So, therefore, the term that I am getting are constant except for this alpha. So, please note I have these alpha terms in this expression. Similarly, when I have phi star phi, I am integrating over all r, theta, phi. So, therefore, I am left with some constants multiplied by some constants and alpha term. So, this integral is a function of alpha, this integral is a function of alpha. So, therefore, the energy value E phi is also a function of alpha, and this is what the functional dependence of energy in terms of alpha looks like for this particular problem. Now, since I know that E phi depends on alpha, I simply obtain the first derivative of it with respect to alpha and then find out at for which value of alpha this equation holds good, and it turns out if you do it, alpha turns out to be 8 divided by 9 pi. Now, my trial wave function was e to the power minus alpha r square. So, this tells me what is the best solution that I would get for if I take my trial function as a Gaussian function instead of a e to the power minus r function. The answer comes is that the best case scenario is that when you consider alpha as 8 by 9 pi. So, that will be the best approximate to the true solution when you make this guess function. So, let us see when I put this value of alpha and calculate the energy, what do I get? I get the energy which is minus 0.424 atomic unit. But what is E0? In this case, see E0 is the ground state energy of hydrogen atom. So, in this case it would be minus h bar square divided by 2 mu a square z square divided by n square. This is the expression that we got from hydrogen atom solution. So, h bar is 1, mu mass of electron, a Bohr's radius, all these terms are 1 in atomic unit. So, therefore, I am left with minus 1 by 2, and z is the nuclear charge 1, n is 1 because I am considering the ground state. So, this energy turns out to be minus 0.5 atomic unit. So, this is the true energy, the exact energy that we know when we have because we have solved this problem exactly. But this energy we are getting minus 0.424 atomic unit when we are taking a trial function here. So, the trial function has brought my energy as close as it could, and you can see the correlation between the two is not extremely satisfying, but not bad either. So, therefore, what we see is that even when we have a functional form of the wave function not so correct, we still can get to a good approximation an estimate of the ground state energy by using variational principle. But one thing that I should make you aware of it is that in variational principle, even if my energy, because see I am minimizing my energy so that so as to go to the ground state energy. So, the energy for a trial function can sometimes be nicely reproduced by using a particular trial function, but the other properties of the system which depends on the wave function. But remember, the wave function contains all the information about the system. Energy is one of the observable that is coming out of this system. So, the state of the system is given by phi, which we are getting. Energy is one particular observable out of it. There are many other properties that we would be interested in getting from the system. In those cases, sometimes you would find that although energy is nicely reproduced by variational principle, the other properties of the system are not. So, this is when that is the case, that means we have to question the trial wave function that we have started with. So, when other properties are not evaluated, then we have to see that whether our trial function makes good sense given the system is. So, therefore, variational principle in this approach requires a lot on the person who is doing this calculation and how he chooses, how one chooses this trial wave function, the functional form of the trial function. So, this becomes very much dependent on the trial function, but now we would we would discuss another case where to a great extent this choice that we are making will be will disappear, and this is what the topic of our next discussion. The next point that we want to make is that how we can use variational principle, where the trial function, instead of calling it as e to the power minus alpha r square or some function with an alpha dependence, what we call is that if I define my trial function as a linear combination of some functions. So, remember, when you are trying to solve this the problem of a complicated system, we know, for example, helium atom has one nucleus, 2 electrons. If you somehow remove one electron, make it helium plus, it will represent like a hydrogen atom. So, therefore, helium atom in a way, effectively speaking, 2 hydrogen atoms fused together. So, therefore, when I am looking for the solution of the helium atom, I would say that maybe it would be a good idea if I can express the trial function of this helium atom as a linear combination of this complete set of functions that I have obtained as the solution of hydrogen atom. For example, so if I am interested in if this is the Hamiltonian that I have, whose solution I do not know, in this case what I am telling is that I can make this trial function as a linear combination of psi i's, where psi i's may be a set of functions. We can sometimes use it as known eigenfunction of a simpler system compared to the complicated system that we are dealing, or psi i's can be a set of functions that we are choosing. So, without losing generality of this expression, we say that let us consider this phi, the trial function, not as a single function, rather as a linear combination of several known functions. So, the known functions are psi i's. So, in this approximation I know psi i's. What I do not know are the c i's, or the coefficient with which I should stitch these psi i's together to get my phi. So, suppose I have this description of the phi. So, I know that E phi is simply let us first evaluate phi, and while doing this, let us say we are restricting our discussion to I equals 2, just for the sake of simplicity, but we can generalize that further. So, this is simply phi star phi d tau. So, what is phi star? So, in this case I can simply use the bracket notation. So, you see C 1 psi 1 plus C 2 psi 2. This is in the bra side. The ket has again same function. So, I can expand it as several terms. So, here the C 1 is in the bra side. So, I bring this C 1 star out. Here C 1 is ket. So, I bring this out. This is mere C 1. So, I have psi 1 plus similarly I would do this as C 1 star C 2 psi 1 psi 2. So, this the first term in the bra side I am taking overlap of the both the terms in the ket, plus I have C 2 star C 1 psi 2 psi 1 plus C 2 star C 2 psi 2 psi 2. So, now you see I have this term C1 square. I call this term as the overlap of psi 1 with itself. So, of course, if psi 1 is one of these known functions that I am starting with, if psi 1 is normalized, of course, this will become 1, but we will keep this S 1 1 for a general explanation. So, then I look at this term. So, this term will be C2 star C2 square S 2 2, which is the overlap of psi 2 with psi 2. So, this S is the overlap integral. This term over here shows me C 1 star C 2 S 1 2 plus C 2 star C 1 S 2 1. So, these S functions are the overlap function integrals that we am getting. So, this is what I am getting from phi phi. Now, let us get. So, similarly, when I get this, I express this in the bra side C 1 psi 1 plus C 2 psi 2, the Hamiltonian operator. So, I see when I can have now terms where it would be C 1 star C 1 psi 1 H psi 1 plus. So, I am looking at C 1 with the other terms psi 1 C 1 star C 2 psi 1 the Hamiltonian psi 2. Similarly, now I am coming to the second term. So, C 2 star C 1 psi 2 the Hamiltonian psi 1 plus finally, C 2 star C 2 now. If I simplify this is we know that when I express this integral like this, I can say that this is the matrix element of this Hamiltonian operator when the corresponding to psi 1 and psi 1 basis function. So, this I am calling as H 1 1. So, these are the energy integrals. So, S are called the overlap integrals, and the H S I j H I j are called the energy integrals, because here the operator is Hamiltonian. So, similarly, I have C 1 star C 2 H 1 2 plus C 2 star C 1 H 2 1 plus C 2 square H 2 2. Now, so H 1 1, H 1 2, H 2 1, H 2 2 all are in principle I can obtain them. Why? Because I know what are they? They are simply the matrix element of an operator Hamiltonian operator when the matrix element is psi 1 the basis function is psi 1 or psi 2. Since I know psi 1 and psi 2 and I know the functional form of the Hamiltonian, so I can compute this energy integrals either analytically or if analytically it is not possible, perhaps numerically through a computer program I can do that, but I will get this as some value. So, once I have this term, you see the energy becomes E becomes and you can write this expression over here, this term and this term over here, then you would see that then you solve this equation and then something interesting that would come out. I am skipping that part of the solution and I am writing down what you would get at the end. You would get when you rewrite that expression, you would get something like this. Look here what we have done. What we have done here is that the previous equation we have rewritten in terms of three matrices here, and then the multiplication of this is 0. So, this is another way of expressing the equation through secular determinants. So, now what you have, let us find out whether we identify all these terms. we know what are these H11. So, this is the energy integral corresponding to basis functions of psi 1 and psi 1. H21 is the energy integral corresponding to basis psi 2 and psi 1, and S2 S11 S22 I am sorry, this should be H2 S22 S11 S21 S12 S22, they are all the overlap integrals. What are C1 C2? The C1 and C2s are the coefficients in our linear combination. So, now what we have got here is that when we express our trial function phi as a linear combination of two functions, we are getting a 2 by 2 secular determinant whose solution we will have to find out. But if I take the trial wave function as a linear combination of n number of functions. So, here instead of having a 2 by 2 determinant, I would actually have an n by n determinant. So, I can keep on changing the values of n, and the solution of this equation, you know that if I can diagonalize this term here, this 2 by 2 matrix here, the eigenvalues would actually come out as E, since I have a 2 by 2 matrix. So, therefore, when I diagonalize it, I will get 2 energy values. I will consider the lowest energy value and find out the eigenfunctions corresponding to that energy value, and the eigenfunctions will be given as in terms of C1 and C2. So, by solving this equation, I would get E, in fact, I would get E1 and E2, and corresponding to E1, I will get a C1. So, C11 and C12, and corresponding to E2, I will get C21 and C22. So, that means once I know these coefficients, I can write down the corresponding wave functions, because I know this wave function is simply C1 psi 1 plus C2 psi 2. So, now this way what we are getting is that we are able to obtain this trial wave function in terms of C1 and C2. So, as soon as we have the C1 and C2s, then we can write down our total wave function, total trial wave function, because that trial function is the linear combination, and the energy anyway comes out because by diagonalization. So, now this is 2 by 2, of course, we can do it by hand. Using computers, we can actually go for very large value of n, for example 1000, 10,000 are easily doable in a standard laptop that you may have. If I have further even larger numbers close to a million or several millions, then we can have several different techniques to diagonalize those large matrices. But then the point is that as long as I have defined this matrix, if I can diagonalize them, I will get the energies, I will get these coefficients, and once I have them, I have an explanation for the trial wave function phi and the energies. So, in this way we can obtain, we can use variational principle to get an approximate solution of a complicated problem, where we can express our trial function as a linear combination of several known functions, and the coefficients of these linear combinations as well as the energy would come out when we solve this n by n secular determinant that we discussed in today's class. So, in next class we will use this concept, that expressing the trial function as a linear combination of known functions for a molecular system, and then we will see how we can use variational principle to obtain the approximate energy and the wave functions for that system. That will be the matter that we will take up in next class. Thank you for your attention.